All right, we're back. We're on page 327. What we're going to be talking about is applications of optimization. So optimization is finding the maximums and minimums. This will be about applying it to things, right? So far we've just done it for functions of usually of x, I think exclusively of x. But it could be anything. And so let's see what we can do. So we're going to start with a problem that does not require calculus. And let's see if we can do it. It's basically an algebra/geometry type problem. So it says a piece of wire of length 10 meters is bent into the shape of a rectangle whose length is 5 times its height. Which dimensions produce the rectangle of maximum area? All right, so I think the best thing to do is draw this. I mean, you definitely know how to solve this, right? You don't really need me, but we're going to do it anyway. So its length is 5 times its height. I don't really spend a lot of time trying to make my diagrams all that accurate, nor really should you, I think. Hold on, I gotta fix it. Well, you don't have to know this. I gotta fix my other computer. Okay, we're good. All right, so length, we have 10 meters total. And then what do we know? Its length is 5 times its height. So if the height is y, and this is x, then I am told that the length is 5 times the height. So x is equal to 5y. Okay, and then I have 10 meters total. So, you could label everything, x and y. So 2x plus 2y equals 10. But then I know that x is equal to 5y, so that's really, let's replace, this x with 5y. And so we get 10, 12y is equal to 10. And then that means that y is equal to 5/6. And if y is equal to 5/6, then x must be equal to 5 times that. So 25/6. And there's like no other options, right? We didn't get a function that we had to like optimize or anything. We just had a really concrete scenario. This is not a calculus problem, right? This is a problem that we could have done way back in probably in pre-algebra, really, if you just like think about it. What we want to deal with is problems that are more open-ended, right? So there's a lot of things that satisfy the condition, and then we need to find the one set of information that optimizes the requirement. So the technique is pretty cut and dry. Like you do the same thing basically every time. You're almost always going to want to sketch a figure if it's not provided for you. Choose variables. That's like a big step. So make sure that you are doing that. Sometimes you do that let statement, let x equal, let y equal. I don't really do that, but it's a better technique than what I use. Find the function, determine an interval if you need one. So that's going to be about a domain thing. So maybe the candidates test is going to play into this, right? Because maybe x can only be between 0 and 30 or something like that. Optimize the function just means find the derivative. Find the critical points, decide which one's a maximum, a minimum, whatever, and then state the answer in the context of the problem. So let's see if we can do this problem. So this is going to be an actual calculus problem, hopefully. And here we go. Piece of wire of length 30 meters is bent into the shape of a rectangle with an isosceles right triangle on top. See the figure. Okay, so I guess that's what I don't know if that's what I would have imagined. I don't know. What length for the bottom horizontal edge produces maximum area? So look at that. That's maximum area is what we are looking for. And then the question is, what length for the bottom horizontal edge produces the maximum area? So we're trying to figure out, basically, what value would this have that would produce the absolute maximum area for this entire figure? So let's pick some variables and see what we can do. So, all right, I'm going to start with, generally speaking, we'll call horizontal things x and vertical things y, given a choice. So I'm going to call this x, which means this dotted line is also x. It's probably going to be relevant, but we don't really know. I'm going to call this unknown y, which means this is also y. I don't need to label both of them, but I usually do because it's easier when you're counting like perimeter and things like that to make sure you get everything. And then this is an isosceles this here is isosceles, right? So is that too thick? I think so. Let's go with this. This is isosceles, which means that these are equal. And so it's, excuse me, if the hypotenuse is x, that's like y root 2. If it was like y root 2, so y root 2 is equal to x. So each of these is x over root 2. X over root 2. Okay, so, well, I should have said z. Let's say that it's z root 2, right? 45, 45, 90, special right triangle. Gosh, wonder if my voice is going. All right, so piece of wire is 30 meters in length. So we knew, let's go back to this thicker thing here. Piece of wire is 30 meters in length. So that means that if I add up the perimeter of this thing, I need to get 30. So it's x plus 2y's plus 2x over root 2 is equal to 30. So it's, you can actually simplify this a little bit. So x plus 2y plus radical 2x is equal to 30. Okay. So all I did was rationalize that, but like, I mean, that was crazy looking. I didn't want to deal with that. So that's one thing. And this, I typically call this a helper function. So this is the, you know, I should highlight. Let's see. I think this is a color I haven't used yet. This is our helper. So it's not what we're trying to optimize, but it's a relationship amongst the variables, right? Because we only know how to do calculus with one variable. So if we have an area function, for example, that's a function of x and y, we can use this helper to get rid of one of the variables, which is almost certainly what we're going to do. So let's see. So the area of this thing is xy for the rectangle plus 1/2 the base times the height. So that's 1/2 x root 2 times x root 2 is x squared over 2. So 1/2 x squared over 2. So plus 1/4 x squared. Okay, so that's the area. Now you can see where the problem comes in. Well, it's not really a problem because we're going to solve it. But our area is a function of two variables. So let's get rid of one of them. Almost everyone gets rid of y when they're given the choice. So here we'll use our helper equation. And we'll say that y is equal to 30 minus x minus root 2x all over 2. Okay, so we can replace our y value with that. And we will be in okay shape. It's not like the greatest shape because this is looking pretty ugly, but we'll have the area as a function of just x, and that's what matters. X 30 minus x minus root 2x all over 2, and then plus 1/4 x squared. Okay, this is our function that we're trying to maximize. So this, I think I was using this color. This is what we want to maximize. I'm trying to highlight this without picking up so that it's all one solid color. We're trying to maximize that, right? So I'm going to find the derivative and find a prime or dA dx, depending on how you want to look at it. Okay, so continue being all over the place. A prime is, so what am I thinking here? I'm thinking that the easiest thing to do is really to expand and then just power rule instead of, I definitely am not using the product rule on this thing. So maybe I'll show that step since I don't want to talk through it 1,000 times. So I get 15x, right? 30 over 2 is 15 times x minus x squared over 2 minus root 2x squared over 2 plus 1/4 x squared. Okay, so let's find the derivative of that. So we're going to get 15 minus 1/2 x minus root 2x plus 1/2 x. minus 1/2. Oh, we got a mistake. Hold on, let's go back. This guy right here is actually just x. Okay, I think that that's our derivative. So now, what should we do? Well, we just need to know when a prime equals 0. A prime equals 0 gives me x equals -15 divided by 1/2. So it's -1/2. So it's negative x plus 1/2 is -1/2 x minus √2. So divided by -1/2 minus √2. Okay, should we simplify that? I'm going to simplify that. So that's going to be x is, multiply the top and the bottom by a negative, and just all the negative signs are gone. So I'm doing that in my mind, and then I'm going to multiply everything I see by 2 and get 30 over 1 plus 2 √2. Whew. Okay, so should I clean this up a little bit? I mean, I feel like there's not, first of all, there's just not a lot of space, right? So did not use my space well. I'm gonna move this up a little bit because I gotta test this. I'd like to move things over too if I could, but I think I can't. All right, should I do a number line? So one issue is I don't know what 30, I bet like, well, I can use like basically 30 as like the upper bound. And if I plug in basically 30, I have no idea. You know what I'm gonna do? I'm gonna use the second derivative test, and then I'm gonna explain something called the lonely critical point theorem. So we only have one critical point here. Let's find a double prime. Whoops, not even using a marker. A double prime is -1 minus √2 plus 1/2, which is less than 0. Okay, so here's the idea. And I wish I had more space for this. Let's do this. Not happy about it, but we're going to put an asterisk here. We're going to go up. I saw some space up here. Let's steal this space. Okay, so I'm going to say, since a prime of 30 over 1 plus 2 √2 equals 0, and a double, what? A double prime is less than 0 for all x. A has a maximum at x equals 30 over 1 plus 2 √2. This is like a gross problem to start with. I apologize. Probably should have thought more about that. But whatever. All right, so here's the key thing. So since x equals 30 over 1 plus 2 √2 is the only critical point, A has absolute max at x equals 30 over 1 plus 2 √2. Okay, what is the logic of this? So first of all, my work is all over the place. Clearly I need to respace these notes, but also clearly I will never do that because I'm not reshooting all these videos. So if there's only one critical point on an interval, then if you are at a maximum, that means since there's only one critical point, that's the only place that the function can change from increasing to decreasing. So if there's only one critical point, and at that critical point there's a relative maximum, it must be the absolute maximum. So this is called the lonely critical point theorem. I've never really seen it written anywhere, but it should be. I've also really never seen it given that name officially. I've just heard it called that, and I've sort of adopted that. So we've used the lonely critical point theorem on this. What I want to do, because this was very messy, I want to go back and kind of like redo this with a calculator and just see if we got it right, basically. So let's see. I'm going to start a new document here. Okay, so we had area as a function of x, we said was x times parentheses 30 minus x minus square root of 2 times x over 2, I think, and then plus 1/4 x squared. Okay, done. We found the derivative. Oh, not the second derivative. Well, we ultimately did find the second derivative, but first we found the derivative with respect to x of a of x. Okay, we set that equal to 0 and solved. And we got, that is a very different looking answer than what I got. But I think what happened is the calculator, I think, rationalized. Maybe. Let's see what our answer was. 30 over 1 plus 2 square root of 2. Yes, the calculator rationalized the answer, so that's unexpected, but it should have been expected because it always rationalizes, which is kind of annoying. Okay, so this is what we got for our x value. So I'm going to store that because I do not want to type that again. Okay, then we found the second derivative with respect to x of a of x. And let me get a decimal. So that is negative. All right, so we have a critical point where the derivative is 0. We have the second derivative is always negative, which means that the function is always concave down, which means that at our critical point where the derivative is 0, we must be at a relative maximum. Then the argument that we made was there's only one critical point, and if at that critical point we're getting a relative maximum, we must be getting the absolute maximum. So we found the length of the horizontal edge that maximizes the area. We didn't find the area because no one is crazy enough to try to do that because of the way this function works. Nobody's going back and doing that. Let's just graph it. A of x. And so we know that x couldn't ever be more than 30. So let's go -5 to 35. And I don't know, negative, like maybe the area is like 50. No, it's bigger than 50. Let's go with, you know what we can do? We can do a of xc and then plus like 10. So xc, I stored that critical point, if you recall. There we go. Okay, pretty good. Oh, check out the maximum y there. That's kind of insane. So you can see there's only one critical point. At the critical point, relative maximum must be the absolute maximum. You can use that. You're going to use it, in fact, a lot because these problems are really annoying to actually do number line tests with. So what I'm going to do is go back to the notes where we crammed in the work for this, which is not unusual. I actually know that happens every year. I just it's always right around the summer when we hit this, and I always mean to fix things, and time gets away from you. All right, so I'm going to stop this video here, come back, do the next problem on this page, and then we are just going to keep rolling. So I will see you then.